Hey there. So in the last video, we talked about quite a few ideas with momentum. So I want to start this video by giving a quick recap of those. So what we set up a system of particles where all of the forces were internal. Or another way of saying that, there were no external forces acting on any of my particles. When we did that, we found that the center of mass of that system did not accelerate. It could have a constant velocity, it could be not moving at all, but the center of mass did not accelerate. And furthermore, we could find that the momentum of that system, where the momentum of the system was defined as the total mass of my system times the velocity of the center of mass, that did not change. Okay? And we called that the conservation of linear momentum. So if I took the time derivative of that, of course, that would be equal to 0. So next, we're going to talk a little bit about external forces. I'm going to follow a very similar procedure that I followed in my last video for this discussion. And in fact, you could probably come up with the same results on your own without even watching this video. But I think it's good either way to reiterate points just for, clarity's sake. So I'm going to go ahead and draw a very similar picture here with the three particles again, but this time I'm going to box only M1 and M2 in my system. Remember, everything in the blue is what's in my system. Everything outside of the blue is what's in my environment. I create position vectors pointing to M1 and M2, the particles of my system. Remember that each of these vectors, R1 and R2, they're functions of time, right? Because these particles are going to be moving around. Remember, if I take the time derivative of my position vector, that is the definition of the velocity for one of those particles. And the second time derivative would be the acceleration of one of those particles. All right, that's all just reminder. Well, I guess here's another reminder. um, F2 comma 1 and F1 comma 2, these guys are internal forces, right? Remember, they're generated by particles that are within the system. That's why they're internal. F3 comma 1 and F3 comma 2, those are generated by the interactions with M3. M3 is outside of our system, therefore F3 comma 1 and F3 comma 2 are external forces. So that's the key assumption, that we have external forces this time. Now, just like in the last video, we create equations of motion for each particle. So, for example, for M1, we have F2 comma 1 plus F3 comma 1, and that equals M1 times its acceleration. Right? Very simple. We do the exact same thing for M2. And now, remember, when we add these things, by Newton's third law, F2 comma 1 and F1 comma 2 are equal and opposite. So those guys are going to cancel out with each other. F3 comma 1 and F3 comma 2, we can't conclude anything about. There's going to be no cancellation between those guys. And so we add these forces together, and we get F3 comma 1 plus F3 comma 2 on the left-hand side, and that equals M1 times R1 double dot plus M2 times R2 double dot. If you remember before, this left-hand side was 0. In this case, it is not. Now let's go ahead and just recognize what this is on the left-hand side. This is the sum of my external forces that are acting on the particles. So I'm going to introduce a little definition here, that whatever my sum of my external forces is acting on each of the little particles, so that would be like this guy and this guy right here, I sum those together and I call that capital F external. This is called my net external force. So with that definition, I just go ahead and I substitute that in. Next, I go ahead and divide both sides of my equation by m1 and plus m2. And then, if you remember from the last video, this guy on the right here, this is the definition of the acceleration of my center of mass. In that video, we talk a lot more about how we define center of mass and show that we can take its derivative to show that this definition is true. Okay, and let's do another categorization and remember that m1 plus m2, that is just the total mass of my entire system. In this case, there's only two particles in my system, that's why it's a very short sum. But, if we had n particles, we would just have more masses being added together. And likewise, again, if we had more particles, we would have more external forces. I'm just using two particles in my system to make this as simple as possible. All right. Next, we can multiply both sides of this equation by m, and we get the following. My net external force equals the total mass of my system times the acceleration of my system's center of mass. We can show that this statement is true for n particles as well. Uh, Again, that's just kind of the point that I made about we can extend these summations out as much as we want, and it's just the same definitions apply and we get the same result. All right, let's go ahead and be very clear about what we concluded here. We summed together all of our little external forces that were acting on each of the particles, and we defined that as the net external force acting on my system. And then we also concluded this statement here that the net external force acting on a system of particles is responsible for accelerating that system's center of mass. So this is going to be very useful because we're able to simplify very complicated systems of particles to a single point, the center of mass. And we're able to just focus on the motion of that one point. If there's no net external force, this F external guy would go to 0, and we would see that the acceleration of that center of mass is 0. And that's what we saw in the last video, when you only had internal forces. This is an even more general statement. All right, next all we're going to do is we're just going to make this look like a statement of P dot of my system. So that's the statement we had from before. And this time I'm going to show that the P of my system is equal to m times r dot center of mass. I started with this statement before in my last video, and I showed that it was a true statement. But this time, let's just go ahead and go the reverse route just to reiterate and be very clear and all of that. So generally, the momentum of my system is defined as just taking the momentum of each particle and adding them all together. So that's just a very basic starting point. Then we can write each of those momentums as follows. m1 times r1 dot plus m2 times r2 dot, yada, yada, yada. It just keeps summing out. All right, perfect. We take this guy, we divide by the mass of the entire system, m1 plus m2, da 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 da, and we multiply by the same deal. And so, on the left-hand side, we still have p system, because really this is just multiplying by 1 on the left-hand side, right? Because those guys would cancel out with each other. And so this is a very simple manipulation we can make, and then we just redefine terms again. So this is the velocity of my center of mass here on the left, and on the right here, that's the total mass of my system. All right, great. So we've shown that the momentum of my system is just the mass of my system times the velocity of my center of mass. Okay, now I take the time derivative of that generically, and I get m times r dot center of mass plus plus m dot times r center of mass. Whoa, 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 whoa. That's not right. This would be the second time derivative here, and this would be the first time derivative there. There we go. Okay. What we really should have had would be that the time derivative of my momentum would be equal to m times r double dot center of mass plus m dot times r dot center of mass. This is just by the product rule. All right, we already showed before that this term right here is just equal to F external, that guy right there. That's a really bad arrow. That's okay. So that's equal to F external. What about this term here? Remember, this guy goes to 0. Why? Because the time derivative of my system's mass, that's going to be 0. The system is a very rigid definition, right? You can't just have particles entering and leaving your system once you have everything defined. The system is defined by the masses that are in that system, right? There's a little point on that. They're called variable mass systems, but you can really show that if you define your system well, there's nothing that's actually variable mass there. So I'll get to that later. Okay. So we come up with this statement that P dot of my system is equal to F external. Right? And you could just read this kind of in English to clarify what it means. You say that the external force acting on my system of particles is responsible for changing that system's momentum. That makes sense. That should make sense very intuitively. So what we've done in all these parts, we've just expanded our knowledge to include external forces uh, in our analysis of systems. And remember that if the forces are all internal, this F goes to 0, this F here goes to 0, and we derive the conservation of momentum again. So this statement here, when my external force is 0, that's the conservation of momentum. This statement here, when I make my external force 0, that shows that the acceleration of my center of mass is 0. Okay? Make sure that we see that. That's consistent with what we already proved in the last video. So I'm just trying to connect all of these ideas together. And I'm going to make sure to do example problems for all of this stuff too. I definitely want to do that. So the next thing that I kind of want to conclude this video with is I just want to talk a little bit about objects and kind of show what this set of videos said about objects. So let's say that I have a block with mass capital M. What we're really saying that that block is it's just a sea of point particles, right? And then we happened to box that in our system. We made a convenient choice for defining our system. And all of these particles are just interacting with each other by internal forces, which are the red arrows here. I tried to color code what I'm saying here. So in this picture, the block has no interaction with the environment. So while all of these point particles are interacting with each other, we know that we could find a center of mass of this block and show that its velocity, uh, or show that its acceleration was zero. I'm getting a little ahead of myself. That's what I should have shown here. So this was from video one, though, defining your system. And then from the second video, we showed that because M doesn't interact with the environment in any way, we show that the momentum of this block, or the momentum of this block is conserved, right? And the acceleration of its center of mass is zero, right? We took this very complicated problem with lots of particles that were jumbling around, and we simplified it to a single point that we called the center of mass. And then in this third video, let's imagine that we took a piston and we pushed it, right? And we pushed the block. Well, what we would be doing is, and I made the piston green to show that it's part of my environment. The system is just my block, right? So we know that the piston only technically acts at the exact point of contact. So only these local particles on the left here are going to be actually exposed to that contact force. And then what happens is I went ahead and zoomed in on like this row up here, kind of like with these guys. And this is a bit of a simplification, but what we can imagine happening is that these particles kind of get pushed together, and internal forces are responsible for pushing then M2 and slowing down M1. And so the internal forces at play here, you can kind of ignore these expressions. These are just the exact internal forces that are necessary for M1 and M2 to accelerate exactly the same together. So for these guys to both have the same acceleration to the right, that's how the forces would have to uh, be between them. I said that sentence a little weird. But I don't want to make this too overly complicated, but I want to be clear that the internal forces between my particles are responsible for kind of distributing out those external forces throughout the block, right? Because again, the only point of contact is super early on here, right? And then the internal forces kind of distribute that out. But anyways, we don't even have to worry about any of that. Because in this video, we showed I could just take all of these guys right here. There we go. I could take all of these guys right here and add them together, right? I just add all of these guys together and I get the net external force. And depending on who you are, you can draw the net external force from your center of mass. I think a lot of people also like to draw the arrows like on the end of the box, uh, kind of like that. Uh, but anyways, that's up to you. Um, so yeah, so we can show that this summation is true, and then we just use our analysis from this video to show that the rate of change of my block's momentum with respect to time, that by definition is the net external force on the block, and that's equal to the total mass of the block times the acceleration of its center of mass. Now, the only thing that I want to, clarify is, okay, so we know that when I apply an external force, that's going to make this center of mass of my block accelerate by some amount. But does a particle in like the top left here, just a random particle in a block, what says that this guy accelerates the same as the center of mass point? Okay? That's kind of the question. And there really is nothing to say that, but I'll just go ahead and make this last point here, that in a perfect block, my external forces get distributed out, again, by the internal forces of the block. In a perfect block, my external forces get distributed so the particles accelerate all exactly the same together. So if this happened, the acceleration of each particle would equal the acceleration of the center of mass. So what do I mean? If this guy was accelerating at 5 meters per second squared, this particle in the top left would also be accelerating at the exact same amount, 5 meters per second squared. That's an ideal case. It's impossible to get this exactly. That being said, the more rigid the object, the closer that the acceleration of my center of mass gets to the acceleration of each particle in the system. So the center of mass analysis is particularly useful when you're looking at rigid objects. Because again, by taking all these particles and reducing them down to one point, you're losing all of the complexity about the motion that each of these individual particles do. But if the object is very rigid, each of their accelerations will be very similar to the acceleration of your center of mass. I hope that last point makes a lot of sense. And I hope that it shows that the center of mass really is a simplification of a complicated problem. Um, all right. So from here, I think I'm just going to do a lot of example problems in future videos because I think just talking about this kind of stuff is kind of dense and a little bit hard to understand. But I really hope I did a decent job at making these points clear and uh, let me know uh, if anything that I'm saying is very, very confusing or anything like that. I'm really trying my best to improve my explanations constantly and, just keep getting better at giving these talks on things. But yes, I'll definitely do examples in the future. So I hope you enjoyed these little talks and thank you so, so much for watching.